Problem statement. Let's say that the adult male height x in a city is approximately normally distributed. Let's say this is given to you with the mean value as 170 centimeter and standard deviation of 8 centimeter. If you randomly pick an adult, you go to the city and you pick one guy, okay, let's say this is the guy you picked, then what is the probability that his height is going to be less than 155 centimeter, greater than 190 centimeter, between 160 and 180 centimeter, and exactly 190 centimeter? So this session is about dealing with these types of problems. So let's try to understand the theory first. Let's say you go to a city and you randomly select 10 people and you measure their weight. Okay, it doesn't have to be weight. You could be measuring their height, their blood pressure, could be anything. So let's say we are measuring their weight and you construct a histogram of only these 10 people. Okay, this is how your histogram will probably look like. Okay, mine looks like this. You could be a little different, but it's going to be something like that. Okay, now what if you increase the number of samples from 10 people to 50 people? Well, this is how your histogram probably will look like. What about 100 people? Okay, and what about 500, 1000, and all the way up to 10,000? Now look at the size of it. Now look at the shape of my histogram. Okay, this shape actually is kind of like weird, doesn't have any particular shape. Okay, but as your sample size is increasing, as you can see, your sample size is increasing, your shape of your curve is becoming like almost like a bell shape. It's taking a proper bell shaped shape right here. It's taking a shape of a bell curve and looks like a bell curve right here. Okay, so this actually is more closer to the bell curve than the rest of the other curves, and that's because the sample size is more very high. So let's look at some of the key points of this curve. The first one is it is a bell-shaped curve. You can just by looking at it, you can tell it is a bell-shaped curve. Number two, it is also called a Gaussian distribution. That's another name for that. The mean, median, and mode, they're equal. So your mean, median, mode, which would be right here, they're equal. They're located exactly at the same place. Okay, they're at the center. The curve is symmetric about the mean. So if this is my mean value, okay, and the curve is symmetric. In other words, the curve on this side, on your left-hand side, is exactly same. It's the mirror copy of the curve on your right-hand side. The curve is continuous. What it means is that when you draw the curve, you're not going to find any holes, any missing values. It will keep, there are always some values over here. Same thing on this side. In other words, another way of saying this thing, if let's say you randomly pick a point x, let's say this is the value of x you pick, you will always be able to find a corresponding y value on the curve. The curve is asymptotic to the x-axis. What it means is that the curve, when you go in this direction, let's say you go in this direction, the curve will keep going, but it's never going to come and touch the x-axis. It will keep coming closer and closer to the x-axis. Same thing in this direction. In literature, sometimes you'll see this curve is denoted with this notation. So this means the x follows a normal distribution. N stands for normal, mu stands for your mean value, and sigma is your standard deviation. The area above an interval, it represents the probability of finding x value in that interval. What it means is this. Let's say this is an interval from A to B. The probability that you will find your x value between A and B is equal to this area right here. Okay, it's equal to the area between the curve and that interval. That's what it means. So the probability of x between a and b is equal to the area between a and b, and that area, if you remember from your class of calculus, you can calculate that using tools from the integration. So these are my this is my integration right here. Okay, this is my function. I'm integrating this function, and that will give me this area right here, this area. The probability of finding an exact x value is 0. In other words, let's say this is your value and you want to find what is the probability that your x value is going to take the value c. C could be anything. It could be 9, 5, 10, doesn't matter what it is. It could be any value. So the probability of x being exactly this value is going to be 0. That's what you mean by this statement. That's what this means right here. The total area under a normal distribution curve is always equal to 1. So if you calculate all this area from here all the way up to here, okay, the total area is going to be equal to 1. That's what it means. In other words, if you think about it, the area represents the probability. So the probability of finding x between minus infinity, okay, to plus infinity is going to be equal to 1, because you will find, like if you think about it, your x will be present somewhere between minus infinity to plus infinity because it has to be present there. Now I'm going to tell you about empirical rules 68, 95, 99.7. This is only applicable if your distribution is normal. The empirical rule says this, that about 68% of your data, approximately 68% of your data, it lies within one standard deviation of the mean. In other words, it lies between mu minus sigma and mu plus sigma. So if this is my mu value, you go sigma in this direction, sigma in this direction. So approximately 68% of my data is going to be lying between here and here. That's what he's saying. Another way of saying this thing is this, that if you calculate this area going from here to here, and if you calculate all this area right here, this area will come out to be 0.68. So this is my 0.68. That's what this means. The next rule, which is 95, which says that about 95% of my data, it lies within two standard deviation of the mean. In other words, between mu minus 2 sigma and mu plus 2 sigma. So if you go 2 sigma in this direction, okay, this is your mu minus 2 sigma, and if you go 2 sigma in this direction, okay, sigma is your standard deviation, then approximately 95% of my data is going to be lying over here in between these two values. So if you calculate the area, okay, same thing, if you calculate the area between here all the way up to there, this area, this whole area right here, all this area, it will come out to be 0.95. That's what this says. The third one says that about 99.7% of my data, it lies within three standard deviation of my mean. In other words, between mu minus 3 sigma and mu plus 3 sigma. So if this is my mu minus 3 sigma right here, okay, and mu plus 3 sigma is over here. In other words, 99.7% of my data is going to be lying in this range right here. Okay, that's what this is. 99.7% of my data lies over here. In other words, if I draw a line like this, okay, and I calculate this area from here all the way up to there, and if I calculate this area is going to be approximately equal to 0.997. Okay, so some of the interesting application of this empirical rule, it kind of helps you quickly estimate the probabilities without doing integration. So let's say somebody asks you, hey, what is the probability that your x lies between mu minus sigma and mu plus sigma, and as long as you know that your distribution is normal, you can just quickly say the answer is 0.68. Same thing with this. Let's say somebody asks you what is the probability that your x lies between between mu minus 2 sigma and mu plus 2 sigma, you can quickly answer. The answer is 95% chance, 0.95. So as long as they're asking you questions which are easy and which are falling in between the standard deviation range, you can actually answer those questions pretty fast. It also helps you identify outliers. So any value that falls outside the range of 3 sigma in this range and in this range, generally they're considered to be outliers. So that's one of the interesting application of this empirical rule. Another one is also to check if your data set is roughly normal. So if your data set is satisfying your empirical rule, okay, if it satisfies this empirical rule, which is this right here, if 68% of your data is lying between one standard deviation and 95% is lying between two standard deviation and 99.7 is lying within three standard deviation, then you can safely conclude that your data is normally distributed. Now, this is for the mathematical oriented students. The mathematical function that describes this curve is given by this expression right here. In this case, your fx is called probability distribution function. Mu is the mean value right here. That's my mean value. Your sigma is the standard deviation. Okay, that's my standard deviation right here. And this actually denotes your spread. And your E is your Euler number. Your pi is this number right here. Now, the key idea in this is this, that your exponential term, which is this term is what is responsible for making making your curve right here symmetric about your mean value. Because of the presence of this term, that's why your curve is symmetric. Also, this one right here, this term, this constant right here, this term is responsible for making sure that your area is equal to 1. So when you calculate your integral of this one, the area comes out to be 1 because of this term right here. Now I'm going to be talking about standard normal distribution. Standard normal distribution is a special case of your normal distribution where your mean equal to 0 and your standard deviation equal to 1. Any normal distribution can be converted into a standard normal distribution. This process is called standardization or normalization. So let's say you have a variable x in your normal distribution. You can convert that into standard normal distribution using this expression right here. Okay. Now, this area, this is your curve. This is called normal distribution. This gets mapped to your standard normal distribution curve. If this is your expression of your normal distribution, this expression gets turned into this expression right here. Likewise, if this is your probability of calculating some value in your normal distribution, then in standard normal distribution, it becomes this expression right here. So all this thing happens because of this mapping right here. Now, this probability can be calculated from a z table that's provided to you. So why do we convert from a normal distribution to the standard normal distribution? Well, the answer is because it simplifies your calculation. We can read the values of the area directly from your z table, which is a lot easier. It also allows us to compare schools from different normal distributions. So let's say you have one school right here. Let's call this thing as school one. Okay, this is your score from the school one, and this normal distribution is from school two. So it can be a little bit hard to compare this from this, right? Because your mean could be different, your standard deviation could be different. Same thing with this school, your mean and standard deviation could be different. So it can be hard. But by converting them, okay, to a standard normal distribution, both of the school you convert to the standard normal distribution, now you have scaled them down. Now you can actually compare these two distribution.